In this module, you will learn about arithmetic progression. As we have learned, a collection of numbers arranged in a definite order according to some definite rule or pattern is called a sequence. Each number in the sequence is called a term, and the term in the nth position is called the nth term. Now, take a look at the patterns in the sequences shown here. Is it possible to write the next term in these sequences? Yes, by following the rule or pattern, it can be done. In the first sequence, a term can be obtained by adding 5 to the term preceding it. That is, the nth term can be obtained by adding the n-1th term and 5, which is the difference between two consecutive terms. Similarly, in the second sequence, each term can be obtained by adding 10 to the term preceding it. That is, the nth term is equal to the n-1th term plus 10. In both the sequences, we see that successive terms are obtained by adding a fixed number to the terms just preceding it. Such sequences are called arithmetic progressions. Mathematically, a sequence is said to be in arithmetic progression if every term, except the first, is obtained by adding a fixed number to its preceding term. The fixed number is called the common difference and is obtained by subtracting any term from its succeeding term. That is, d is equal to the nth term minus the n-1th term. The general form of an arithmetic progression is of the form a plus d, a plus 2d, a plus 3d, a plus 4d, and so on, where a is the first term and d is the common difference. Here a plus d is the second term, a plus 2d is the third term, a plus 3d is the fourth term, and so on. Likewise, the nth term, which is also known as the general term, is denoted by a with the subscript n and is equal to a plus n-1 into d. With the help of this general term or nth term, we can find out any required term in the sequence without actually finding the preceding terms. The sum of the first n terms of an arithmetic progression is n by 2 into 2a plus n-1 into d, or n by 2 into a plus l, where l is the nth term or the last term of the arithmetic progression. Now, let us verify some properties of an arithmetic progression one by one. First is, if a constant is added to each term of an arithmetic progression, then the resulting sequence is also an arithmetic progression. Consider an arithmetic progression with the terms 2, 4, 6, 8, and so on. On adding 3 to each term of the given sequence, the resultant sequence is 5, 7, 9, 11, and so on. Observe that the resultant sequence is also an arithmetic progression with the first term 5 and the common difference 2. That is, the common difference of the resultant series is equal to the common difference of the original series. Similarly, if a constant is subtracted from each term of an AP, the resulting sequence is also an AP. Next, if each term of an arithmetic progression is multiplied by a constant, then the resulting sequence is also an arithmetic progression. For example, let 5, 8, 11, 14, and so on be an arithmetic progression. Its common difference is 3. If we multiply each term of this sequence by 2, then the resulting sequence 10, 16, 22, 28 and so on is also an arithmetic progression with the common difference 6. Observe that the common difference of the resultant sequence is also a multiple of the number with which the sequence is multiplied. Similarly, if each term of an arithmetic progression is divided by a non-zero constant, then the resulting sequence is also an arithmetic progression. If the corresponding terms of two arithmetic progressions are added, then the resulting sequence is also an arithmetic progression. Let us consider two arithmetic progressions, 2, 4, 6, 8 and so on, and 3, 5, 7, 9 and so on. On adding the corresponding terms of two arithmetic progressions, we get the sequence of terms 5, 9, 13, 17 and so on. This is also an arithmetic progression. Observe that the common difference of the resultant sequence is the sum of the common differences of the two given arithmetic progressions. Similarly, if the corresponding terms of two arithmetic progressions are subtracted, then the resulting sequence is also an arithmetic progression, provided that the common difference of the two given sequences is not the same. Let us now prove one more result. That is, if the nth term of any sequence is a linear expression in n, then the sequence is an arithmetic progression. Let the nth term of the sequence be equal to an plus b, where a and b are real constants and n is equal to 1, 2, 3 and so on. For n is equal to 1, we have the first term as a plus b. For n is equal to 2, we have the second term as 2a plus b. For n is equal to 3, the third term is 3a plus b. Similarly, n minus 1th term is equal to a into n minus 1 plus b. Now, let's find the difference between consecutive terms. T2 minus T1 is equal to a. T3 minus T2 is equal to a, and so on. Lastly, the nth term minus the n minus 1th term is also equal to a. Therefore, the common difference of the sequence T1, T2, T3 and so on up to Tn is a, which is a constant. Hence, a sequence whose nth term is a linear expression in n forms an AP. Let us now learn to form an arithmetic progression by inserting the desired number of terms between any two terms. Given two numbers a and b, we can find a number c midway between them such that the resulting sequence of the three numbers forms an arithmetic progression. That is, we can find a number c such that c minus a is equal to b minus c, or c is equal to a plus b upon 2. Such a number c is called the arithmetic mean of the numbers a and b. Mathematically, the arithmetic mean between two numbers is a number that, when placed between them, forms with them an arithmetic progression. It is denoted by capital AM. In general, we can insert any number of terms between two given terms such that the resulting sequence is an arithmetic progression. Let us insert n terms between a and b such that the resulting sequence forms an arithmetic progression. This resulting arithmetic progression has n plus 2 terms, where a is the first term and b is the n plus 2th term. Now, the n plus 2th term is b. This implies a plus of n plus 2 minus 1 into d is equal to b. It further implies that d is equal to b minus a upon n plus 1. Now the inserted terms can be obtained by adding d successively to the first term. Let us consider one example. Insert 4 numbers between 2 and 32 such that the resulting sequence is an arithmetic progression. Let A1, A2, A3 and A4 be the 4 numbers between 2 and 32 such that 2, A1, A2, A3, A4 and 32 form an arithmetic progression. There are 6 terms in this sequence. Using the formula for the nth term, the 6th term, 32, is equal to 2 plus of 6 minus 1 into d. On simplifying, we get d is equal to 6. Thus, A1 is equal to 2 plus d, which is equal to 8. A2 is equal to 2 plus 2d, which is equal to 14. A3 is equal to 2 plus 3d, which is equal to 20. A4 is equal to 2 plus 4d, which is equal to 26. Hence, the 4 numbers between 2 and 32 such that the resulting sequence forms an arithmetic progression are 8, 14, 20 and 26.